So, I've been coming to this meeting okay, intermittently, but quite often. The one thing one can say is getting better all the time. But this meeting, of course, is exceptionally smoothly organized. The reason is very clear. It's the postdocs who conducted it. They're much better at this sort of stuff than all of us. Keep it up. Okay, good. I'm going to talk about a problem which is, I think, sort of simple to state. And that is the following. You have a fluctuating surface. It could be fluctuating in one place or it could be moving, and you put a particle on it and the particle slides down the surface slopes, gravity. Falls into a valley, but because of fluctuations, the valley will become a hill, so the particle will continue moving in some way. Valleys to hills, what have you. Okay, so this is the sort of thing I want to discuss, except I'm going to talk about two particles. The particles don't interact with each other. I mean, no force between them. But in fact, they do get correlated. They get correlated not because of interactions, but because they share the history. It's an environment which is fluctuating. It's the same environment for both. They're not at the same places, but you can see shared histories imply correlations. Okay, all right. So where do I point this? Anyway, right. Okay, good. No, so all I wanted to say is, yeah, so the sorts of interfaces I'll talk about are exceptionally simple and well studied. These are one-dimensional models, and broadly, there are two important universality classes. Depending on whether, if you have a height field that tells you what the interface is like, whether you have a symmetry between up and down, in which case the generic model is the Edwards-Wilkinson model. Or it could be that you don't have an H to A minus H symmetry. For instance, if this interface is pushed or it's growing, in which case you generate additional nonlinear terms. And the generic model here is the Kardar-Parisi-Zhang or KPZ model. So these are very well studied. One knows not only the critical exponents, but also the scaling functions of both these systems. And, they're of course very different. The dynamic exponent is 2 for Edwards-Wilkinson, 3 by 2 here. But now the question is, we have this thing. What about particles that are put on the screen? Can we say something about the dynamics of particles? Okay, so here we are. The dynamics I'm considering is over-damped dynamics. So the particles don't accelerate as they fall. They reach a terminal velocity, they fall down. And here's a schematic depiction of the model. It's a lattice model which belongs to the universality classes that I talked about earlier. So it's a model made up of bonds and sites, and at the sites there are particles which are shown in red. They're non-interacting and they just fall down. The surface itself evolves, and the important thing is that it evolves autonomously. Meaning, autonomous means that the particles don't affect it. So the particles are passive in that sense. They're affected by the surface, but they don't act back. And so this is an example of a well-studied large problem in many areas of physics. It's called the passive scalar problem. This is a particularly simple example. The lattice models evolve in some way through stochastic rules. The lattice, for instance, in this KPZ advection case, as it's called, the only allowed moves are small hills going to valleys. If both are allowed, then you have H to minus H symmetry. You have Edwards-Wilkinson driving. And here, it's the same as that, except the surface moves upwards, whereas particles fall downward. This was a case suggested many years ago by Kardar and Russell. That it's interesting because of some applications which I won't discuss now. It's called anti-advection. When the surface is falling and the particles also falling down, they get trapped quite well. It's advection. The other way, also get trapped not so well, anti-advection, and in between is Edwards-Wilkinson. Well, okay. So what happens? I don't know if this is visible. Is it? Okay, good. So this is what happens. See, basically what happens if you have lots of particles is there's a clustering. Particles are driven together. Okay? The degree of clustering varies from one dynamics to the other. As you can see, it's quite intense in the case of KPZ advection. So here we've started with something that is uniformly spread across the lattice. Very quickly it combines into clusters which then merge with each other. And of course, it's not a perfect cluster in the sense that, it can break, does break a little. It is quite localized until it reaches some point when it actually breaks into two, but those two will combine later. Okay, here is Edwards-Wilkinson driving, and you can see it's much more patchy. It's not so well collected, but you can still see large regions of black. Black means no particles. If there are no particles there, then they must be clustered somewhere else, and they are. Likewise with anti-advection. Now, clearly the first question to ask is what happens with a single particle? What happens if you have just one particle? How far does it go? And this has been studied for a number of years, starting with, Warren Pekowski in 1993, Kardar, etc., and there are answers that are known. One qualitative question you can ask. The surface has its own dynamic exponent. Will it force the particle to do the same? Is it slaved? The answer is yes, only for KPZ advection. The other cases like anti-advection made this same error again, which I did some time back. This is 1 over z is 0.57. Sorry about that. 1.74 is the number. I remember Chandan pointing this out in some earlier talk, and here he is again. So before he can do it, yeah, sorry. An older slide, yeah, okay. Right. And you can see that it's slaved in the sense that these are equal in the KPZ case, certainly not here. With Edwards-Wilkinson driving, it seems most likely that Z is 2 still, but with logarithmic correction. So if L of t is the distance moved in time t, there's a logarithmic correction. Hubenes and Manoj, many years back, I think he's at the back somewhere, has seen this. And we actually did some work. I forgot to mention, of course, all this work is done with Tapas Singh, postdoc. Would have been here and conducted one session, but he's not. All right. But anyway, so yeah. So there are probably log corrections. This is a single particle. Our question really, in the remaining time, however much there is, is what happens with two particles? And the question is interesting because this was studied a few years back by Ueda and Sasa, and they pointed out something which seems contradictory. They pointed out that the mean squared separation of the two particles grows linearly in time, reminds you of a random walk. However, in a random walk, if you ask what is the probability that the two particles are very close by, that will fall as 1 over square root of t in time. But this does not fall, it reaches a finite value. There's a finite probability, substantial probability, that the particles are very close together. Yet the mean square displacement grows linearly in time. So this was Ueda and Sasa. And they pointed out, well, so they tried also to say, so this, that maybe the probability that, you have a separation r at time t behaves in some way as a stretched exponential, and they had some numerical work. We actually want to say that this is not the case. In fact, there's a much simpler scaling description of the whole thing. Here it is. What we are advocating is that there's a simple scaling power law scaling, not stretched exponentials. That's at the behind this. The time is totally up. Okay. You know, with these postdocs, you can't argue. Okay, sorry. All right. Okay, what shall I say? Wanted to say one thing. Let me just say it. Okay, there's a very complete scaling description. The point is the probability that two particles are distant r apart, since they're non-interacting, is the same as the density correlation function with lots of particles, except for trivial factor. That has been shown earlier work, which we had done many years ago, to be a scaling function, and so is this, and this explains the separation data of Ueda and Sasa. It also explains why the R squared grows like T. It also explains why, when two particles are close by, the probability of having that is finite. I mean, since I'm out of time, I won't say more. We'll skip this. There was a suggestion by Ueda that you have replica symmetry breaking. This system, in terms of this, we have some data which seems to go against that, but I'll leave you with the conclusion. And the conclusion just shows a typical trajectory. And the green and the red, I believe, are the trajectories, but by trajectory I mean the separations as a function of time. Look at the green one. Well, mostly they're very close, sometimes a little bit away, but then they go away. And when they go out with a vengeance. And they come back and continue. So both things are true, this and that. Okay, thank you.
Yeah, time for questions.
Burgers part is certainly correct because it's KPZ which master burgers. Can you define Taylor's maybe at lunch, and then I'll give you an answer, hopefully.
Yeah, more questions?
Particles. So the surface will also modify the fluctuation spectrum of surface as well?
Yes, we do consider it in other work.
Oh, I see.
And then interesting things can happen because then the surface modifications can lead to instabilities. So it's a coupled driven diffusive system. You have a 2 by 2 matrix. You have real eigenvalues, the propagating modes, sound waves. If there's a complex eigenvalue, that's an instability. And we know what the final stable state is, it's phase separated. That's a broad answer.
If there is no more question, let's thank Mustansir and all the speakers of the session.